This is Daniel Coosbury, and in this video we're going to take another look at the central limit theorem and apply it to the sample proportion now. So you'll find a lot of the stuff in this video will be familiar to the normal distribution problems we did and the other central limit theorem problems with the sample mean. We're going to just take a look at the sample proportion and find some probabilities. We are incredibly close to being able to do some estimating for the population mean and proportion using this stuff, but that's kind of where we're headed. So let's look real quick at this idea of sampling distribution again. So here's this population, and imagine taking a bunch of different samples of the population, and for each sample I might want to look at the proportion of people or proportion of things in a certain group. So imagine taking one sample, finding the sample proportion. Take a different sample of the same size, you can take another sample proportion. Maybe take a third sample and you can find a sample proportion. And the idea is if all these samples are random, then all these sample proportions are also going to be random, which is how we can say that p hat, the sample proportion, is a random variable. So p hat's a random variable, which means that it has its own special probability distribution, so just like with x bar being a random variable has its own distribution, p hat has its own too. We'll call that the sampling distribution of p hat. So we can find the proportion of people in a category just from taking a sample and calculating the proportion. But we could also, if we know enough things about the population, we could do some probabilities with the proportion as well, just like with the sample mean. Let's go ahead and look at the central limit theorem for p hat. So let's let p hat be the sample proportion for a sample of size n from a population with a known proportion p. So in order to use this, we're going to need to know what the population proportion is. So this is a parameter, whereas this is the statistic that we're looking for. So this is to the population as that is to the sample. We have some conditions just like the last central limit theorem we saw. The conditions to use this are if n times p is greater than or equal to 10, and if n times 1 minus p is also greater than or equal to 10, then the distribution of p hat is approximately normal with mean that and the standard deviation that. So our conditions are if our sample size times our population proportion is greater than or equal to 10, and our sample size times 1 minus the population proportion is also greater than, so this is an and, by the way, these both have to be true, then the distribution is approximately normal, which is good. We wouldn't have much to do if this wasn't normal, so it's a good thing it's normal. With mean p and standard deviation, the square root of p times 1 minus p over n. And another way to write that is like down here. So if this is true and that is true, then p is normal, p hat's normal with mean this and standard deviation that. So by now I hope you're comfortable with finding normal probabilities with the mean and the standard deviation given to you, or if you can find it. But if you know what these two things are, we can find normal probabilities using the normal CDF command in the calculator or using the table A2. So this is really helpful in practice because we'll be able to find probabilities using this is the mean and this is the standard deviation. Okay, so let's go ahead and do this. Approximately 60% of eligible voters voted in the 2016 United States presidential election. In other words, this is what we're pretty sure of all the eligible voters, approximately 60% voted. This is our population proportion. See, there's no sample taken yet. This is of the population of eligible voters. This is the proportion that voted. So this is the population proportion. We're going to poll a sample of 88 eligible voters. So we're taking a sample now. This is our sample size n of 88 eligible voters. And we want to find the probability that more than 80% of the voters in the sample actually voted in 2016. So we want to find the probability that p hat is greater than or equal to 0.8. There's no equal to, doesn't matter, but it just says more than, so more than 80%. Now when we do this kind of math with proportions we don't want to use the percentage, we want to use the proportion. So move the decimal to the left to get that number. Before I can do anything, I need to know that I can use the central limit theorem. In other words, just like with the sample mean, I need to know the population was normal or that n was greater than or equal to 30. To do that, I need to check that n times p is greater than 10, and n times 1 minus p is also greater than 10. So I got n times p, which is 0.6. Are you okay calling this p, population proportion? So this needs to be greater than or equal to 10. I also need n times 1 minus p, which is this. Are you okay with calling 0.4 1 minus p? So I need to check these two conditions or else I can't use the central limit theorem. So I need to check that 88 times 0.6 is greater than 10. It is. I need to check that 88 times 0.4 is also greater than 10. And it is. So we're good in both cases. So this is just a condition to make sure the sample size is big enough. Because in general with statistics, if your sample size is big enough, you can treat things like they're normal and you don't have any problem. So this is just really checking that 88 is big enough for the proportion we're talking about. So this means that then the central limit theorem tells us that mu, the mean of p hat, is going to be equal to p, which is 80%. I'm sorry, 60%. That's p. This is p. This thing. This 60%. And the standard deviation of p hat is going to be equal to the square root of p times 1 minus p all over n, which is 88. So I got to find this number, but this is going to be the standard deviation we use when we do this normal calculation. So I'm going to do the square root of 0.6 times 1 minus 0.6, which is also 0.4, all over 88, all in the square root. And I get 0.5222222. So I'm going to round that to 2 decimals. I'm just going to round that to 0.5. 0.5. Let me round that to that's 0.05. I'm sorry. That's fine. 2 decimals. 0.05. Good. 2 decimals. Okay, so now I have this, which means I can say that p hat is normally distributed with mean 0.6 and standard deviation 0.05. In other words, I've just taken these two formulas from the central limit theorem and said this is my mean and this is my standard deviation. My mean is 0.6, that's p. My standard deviation is 0.0005. So just to make it clear what I'm doing. This is the same kind of thing we did with the sample mean. It's just the formula is different. So that means on my normal graph, I can put my mean as 0.6, my standard deviation 0.05, which means that like 0.8 will be probably out here somewhere. I know that most of my data is within 3 standard deviations, so around 0.75. This is bigger than 0.75. And I want to find the probability that more than 80% voted, which is going to be that little red sliver. I think it's going to be little. I'm going to do normal CDF with left bound 0.8. Let's do right bound 9999999. The mean is 0.6 and the standard deviation 0.05. And I got that from right here because I calculated those things right there. This is my left bound, the greater than 0.8, and my right bound, it goes up forever, all the way to positive infinity. So I'll do this the same way I've been doing normal probabilities this whole time. So I hope you see this feeling like a normal problem, like a normal distribution problem. The difference is I've got to find the distribution for p hat before I do much else. 0.6 and my standard deviation is 0.05. If I do that, I get a very small number. In fact, this is actually less than 0.0001. So this is this number. It's really small. Oftentimes when you're doing probability for statistics, if this is less than 0.001, you can just write something like that. But another way to write this, if you're going to round to 5 decimal places, would be like 0.00003. So it's in 5 decimals. because you go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Which sometimes you summarize it like that. Point is, this is how you do the normal distribution problems. You find the mean, you find the standard deviation, and then you treat it like any other normal problem for the central limit theorem of p hat. Okay, here's a new question. Same situation. Would it be unusual if less than half of the voters in the sample voted? Okay, so I want to find the probability that less than half of the voters voted. In other words, the probability that my sample proportion is less than 1/2. Okay, so this is it. And the question really, is it unusual, yes or no? So we're going to see what this probability really is. We know the mean's 0.6, and I want to see the chance that it's less than 0.5. It's probably right there-ish. And let's just remind ourselves that the mean of p hat is 0.6. The standard deviation of p hat we found using this formula 0.6 times 1 minus 0.6 over 88. And we found that to be 0.05. So that's the mean and the standard deviation that I'm using when I do my normal CDF stuff. And frankly, any problem with this situation is going to use that mean and that's its standard deviation. So this is normal CDF. I need a left bound and a right bound. I'm doing less than 1/2. So my left bound will be negative 9999. And my right bound is going to be 0.5. The mean is 0.6, and the standard deviation is 0.05. I hope you're tired of doing normal problems because you've done so many and you're so good at them that this is just starting to get boring. I hope that you've done enough that this is just very, very familiar, which is why it may not be interesting anymore. But that would be a good thing if it's like really familiar. That's my upper bound, lower bound, 0.6, standard deviation 0.05. And I get 0.022, I'll round that up to 8, 0.0228 as my answer. That's the probability I get less than 1/2. And I use the mu p hat and the sigma p hat. And the question was, is it unusual if less than half voted? We said unusual was going to be less than 0.05. This is less than 0.05, so yes, because this is less than 0.05. It would be unusual if less than half the people in the sample voted. It would be very strange. Let's look at another one. I kind of want to skip this one. Is it okay if I skip this one? So we're going to find the probability that p hat is between 0.7 and 0.8. So you're going to find that using the normal CDF. Use that mu p is equal to 0.6, and that sigma p hat is equal to, I'm just writing this over and over again so that you get used to it. This is equal to 0.05. So use the normal CDF. That's your left bound, that's your right bound. And you get that answer. Let's go ahead and find percentiles now. So I'm looking for the 45th percentile for p hat. I know that my mean is 0.6, and I'm trying to find the number that will separate the lower 45%. This is P45. It's on the number line. From the upper 55%, which will be like all this stuff. So I'm trying to separate the white region from the red stripe region. And I know that my mu p hat is equal to 0.6, and my sigma p hat is equal to 0.05 because I computed it. So I'm going to do the inverse norm thing, where my area to the left of this thing is 0.45. So if you've done a few of these percentile problems, you'll notice there's some nice things going on right here. Those for percentiles, those are always going to be the same. Just move the decimal. 0.45. My mean is going to be 0.6. My standard deviation is going to be 0.05. And that'll tell you what this value is. It's going to be a little bit less than 0.6. You can just kind of tell from the picture. A little bit less than 0.6. Let's do inverse norm. Area to the left is 0.45. Mean is 0.6. Standard deviation is 0.05. And you get 0.59. Yeah. I'm going to go ahead and write 4 decimals here. 0.5937. In other words, it's almost 0.6. So the 45th percentile isn't very interesting, but we're saying that that 45% of the folks, I'm sorry, that if you're, what we're really saying is if you were to take a bunch of samples of size 88, this much of it would be, or 45% of those samples would have proportions less than this, and 55% of those samples will have proportions bigger than this. So the thing is, you find the percentile the same way you find percentiles for X bar and with other things with a normal distribution. Use the inverse norm because you're finding something on the number line, and make sure you have the right mu sub p hat and sigma sub p hat using those formulas from the central limit theorem. So what makes this different from the one with X bar is X bar has a different mean and standard deviation than p hat. But the methods of solving the problems are exactly the same. So you just use the normal distribution, use normal CDF to find probabilities, use the inverse norm to find the numbers on the number line, namely the percentiles. And then these proportion problems feel a lot like all the other normal